So we'll continue with a couple of useful properties of definite integrals. Using the same numbering as before, we have property number 5. If f of x is an odd function, so that means that f of minus x is minus f of x, then the integral of f of x dx from minus a to a is 0. You can either derive this from the definition, or you can look at the graph of the function to see why that is the case. So an odd function is one that is symmetric around the origin, and if this is a and this is minus a here, then what we have is that these two areas are the same. So a1 and a2 are the same. And we know that the integral from minus a to a, if we write it out in terms of integral, in terms of areas, this is negative area 1 plus area 2. But now since they're the same, that's negative area 1 plus area 1, so that is 0. There's a similar property for even functions. If f of x is even, so that means that f of minus x is f of x. That's what even means. Then the integral between two symmetric boundaries, minus a and a, is no longer 0, but is equal to 2 times the integral from 0 to a. Sometimes you can save yourself a bit of work with this rule, because evaluating the integral at 0 usually is a little bit simpler. And the intuition for that rule is similar to the one for odd functions. So an even function is one that is symmetric for rotation around the y-axis. Then let's say this is minus a and this is plus a. Then we see that again these two areas are the same. a1, a2 are the same. So the integral on the left hand side here is a1 plus a2, because the function in this case is above the x-axis, and that then is a1 plus, or a2 plus a2, 2 times a2, and a2 we can also write as the integral from 0 to a f of x dx. Now another useful property is the so-called King's rule. And King's rule, what it basically says is that it doesn't matter if you integrate from the left to the right or from the right to the left. And what do we mean by that? Well, this is our property number 7. If we take the integral from 0 to a f of x dx, that is the same as the integral from 0 to a of f of a minus x dx. And here the intuition, it's not a full proof, but it's an intuition. We have our function f of x here, is that if this is a here, then the left hand side basically tells us what we get if we integrate from 0 to a. And the right hand side tells us what happens if we integrate from a to 0. And you can sort of imagine that if you start from the left or if you start from the right, you get the same area, and that is why the integrals are also the same. This is not enough to call it a full proof, but we can prove the relation formally using the definition as follows. So we'll take the left-hand side, 0 to a f of a minus x dx, and we'll call what you have in the argument here, a minus x, we'll call that t. So let's t be a minus x. So then what we also have is that x is equal to a minus t. And we're going to use that to rewrite our integral. So first of all, we'll put the definition of t in the argument here. So we get f of t. And now we'll have a look at the bounds. So for the bounds, we know that if x is equal to 0, then t is equal to a. And if x is equal to a, then t is equal to 0. So that tells us that the bound 0 here will become a when we write things in terms of t, and the a bound for x will likewise become 0 when we talk about t. And now the last thing that we have to put in our integral is the differential. So let's also do that. And for the differential d of x, so that's not a very visible color, let me switch back to black here. There's a special rule, so we can transform the differential like this. We can say the differential of x is the derivative of x divided by, or the derivative of x with respect to t, times the differential with respect to t. And we know what x is as a function of t, so it's a minus t. If we take the derivative with respect to t, we get minus 1 dt. And so this is quite an important rule, and we'll see many examples of this later on when we talk about integration by substitution. But for now, as an illustration, we have that rule here. So we have minus dt here. Put parentheses around it. And so now we can clean that up a bit. We get minus f of t dt from a to 0. And now we can use a property to say that we can switch the lower and the upper bounds, but then the sign changes to write this as the integral 0 to a f of t dt. And now the last thing is, you might say, well, here we have integral with respect to t, and originally we had integral with respect to x. So that's a very special property of definite integrals. The variable that you integrate against, you can name that whatever you want. So we can rename that to x if we wanted to. So the definite integral is always a number, so that whatever you have here disappears from the final result. So you can rename it to x if you want to. There's a second property, I'll call it 7 prime, that is very similar. That says that the integral a to b f of x dx is equal to integral a b f of a plus b minus x dx. And the proof and the interpretation are exactly the same, so I will leave this to you to check this, please. So before we dive into some examples, let's have a look at the assumptions that we made when implicitly defining the integral. And there's one implicit assumption that we made, is that f of x is continuous on the interval a, b. But you can define the integral also for functions that are not necessarily continuous, and exactly how far you can take it is a bit beyond the scope of this course. But in particular, the integral makes sense for functions that are not continuous but are piecewise continuous. So can also define the the integral if f of x is piecewise continuous. And what do we mean by that? Well, a piecewise continuous function is one that is continuous except for a couple of points where it has a jump. So like this, it's mostly continuous, but once in a while it makes a jump. So let's call these points A and B, and then let's call the points where it makes a jump. Let's say that is P, Q, and R. Then how do you define the integral of such a function? Well, you probably already see it if you think in terms of areas. What we can do is we can just integrate up until the point where we have a jump, so integral from A to P, because the function is nice and continuous there, this area, and then integrate from P to Q. That gives us this area. Integrate from Q to R. That gives us this area. And then finally from R to B. And that gives us this area. So if you have a piecewise continuous function, you just have to determine the points where it jumps, where it's not continuous, and then divide up your integral to take each of those breakpoints into account. So with that, let's look at a couple of examples. So first, let's compute the indefinite integral of 10 times x to the power 4 minus 2 divided by square root of 1 minus x squared dx. And we can use our linearity here to write this as x to the power 4 dx minus 2 times dx 1 over square root of 1 minus x squared. And now these are integrals that we can make sense of. So x to the power 4, that gives us x to the 5 divided by 5. And square root of 1 minus x squared, that gives us an inverse sign. And then we have to add a constant. Don't forget the constant. In other words, it's 2x to the 5 minus 2 times sine inverse plus c. Secondly, let's have a look at the definite integral 0 to 1 x to the power 5 over 2 1 minus x dx. So with integrals, if you have this nice factorization, it makes sense to undo the factorization and write this as x to the 5 halves minus x to the 7 halves dx, because now you can write this nicely as integral x to the 5 halves minus integral x to the 7 over 2. And here we can use our rule that says that x of a power, the integral is x to 1 plus that power, so 7 halves, divided by the new exponent, 7 halves, and then evaluate that 1 and 0. And minus, same thing here, x to the 9 halves divided by 9 over 2, evaluate that 1 and 0. So we get 1 over 7 halves minus 1 over 9 halves, which is 2 divided by 7 minus 2 divided by 9. And if you calculate that out, you get 4 divided by 63. Third, let's look at the integral again, indefinite integral of x squared dx 1 plus x squared. This is not a form that we can solve, but if you look at this for a little bit and you try different things, then you might figure out that, hey, there's an x squared in the numerator and there's an x squared in the denominator. So let's try writing that as x squared plus 1 minus 1, 1 plus x squared dx, because now the integral becomes x squared plus 1 divided by x squared plus 1 dx minus integral of dx x squared plus 1, and of course this fraction is 1, integral of 1, that's x, and integral of x squared plus 1, that is the inverse tangent function, so we get x minus tan inverse of x plus a constant. We have a couple of examples that are maybe not so difficult to calculate, but they require thinking a little bit about what we're trying to calculate. So for 4a, what I'm going to do is give you a function g of x, which is the integral 1 to x of the logarithm of y integrated with respect to y dy. And given that function, we want to find g prime of y, so we want to find the derivative of g. And there's a couple of things to be careful about. First of all, the x appears in the upper integration bound, so that's quite new. And then secondly, in the function prescription, we're computing the integral of the logarithm. Right now, we don't have a rule to compute the integral of a logarithm. Later on, we will. But you might ask yourself, well, okay, how then do we compute this integral? And the answer is, well, you have to be a bit careful. We don't really care about the function g of x. That's not what we have to compute. We have to compute the derivative g of x. Sorry, here this should be g of x, g prime of x. So in order to do that, let's go back to our definitions of definite and indefinite integrals, and let's see if we can make sense of this. So for the definite integral, we have that the definite integral is what you get is if you take a antiderivative and you evaluate it at the upper minus the lower bound. So here, where f is the antiderivative of ln x dx. So remember, this is an antiderivative, and what does that mean? Well, if you take the derivative of f of x, then you get your original function back. So that's what it means to be an antiderivative. And then let's have a look at what we have on the left here. Let's take the derivative of this whole expression. So this is my g of x. So then I get d dx of g of x is d dx of that integral, and that's d dx of f of x minus d dx of f of 1. That last thing, f of 1 is a constant, so this is 0. And then d dx of f of x, we just established this is ln of x. And so now that gives us our derivative in one go without computing it. So we have that g prime of x is ln of x. And so the important thing is here that we do not have to compute the integral directly. So if you're careful about what you have to compute, sometimes you can save yourself a lot of work. And then a slight variation on this. Now let's assume that we have a function h of x, which is integral 1 to x squared of ln y dy, and now find h, the derivative again, h prime of x. And now it's almost the same problem, but we have an x squared in the upper integration bound. So we can't say that the derivative of h is just the integrand again, but what we can do is we can use the chain rule. So here we can say, well, h of x is actually g of x squared, where g is the function that we computed originally. And so in particular, we know that g prime of x is ln of x. And now the chain rule tells us that h prime of x is equal to g prime of x squared times d dx of the inner function, so x squared. And so g prime, that's the logarithm of x squared, so we get logarithm ln x squared times the derivative of x squared, so that's times 2x. For the last example, this is a slightly trickier example. And this is an example of why King's rule with the substitution is sometimes useful. So this is slightly complex or complicated, and it uses King's rule. And just to show you that sometimes these simple rules can give you a lot of power when you try to compute something. So let's try to compute the integral 0 to pi over 2 of sine x divided by sine x plus cosine x dx. Again, this is not an integral that we have a rule for, and even with the rules that we will establish in later videos, this might be quite complex. What you can do instead is, and this is a trick that you have to see, and this is partly why integration is a difficult subject. So here you can use King's rule, and we know that the rule says that 0 to a integral is equal to integral of f of x a minus x, again 0 to a. So what that gives us here is that the integral transforms into 0 to pi over 2 sine pi over 2 minus x divided by sine pi over 2 minus x plus cosine pi over 2 minus x dx. And this might look even more complex than what we started from, but now let's use our trigonometry formulas and write this as integral of cosine x in the numerator and then cosine x plus sine x dx. This looks very similar to what we started from, except we have a cosine in the numerator and we started from a sine originally. So let's try to work towards that, or let's try to manipulate this integral a bit further. And what we can do is, now we can write this as integral 0 to pi over 2 cosine x, and I'm going to add the cosine and sine and subtract the sine. And now I can write this as integral of cosine x plus sine x divided by cosine x plus sine x dx, and now minus 0 to pi over 2 sine x cosine x plus sine x dx. And now the integrand here is 1. So here on the left I have integral of 1 dx 0 to 2 pi, so that's going to give me pi over 2. And then the other term I'm going to copy verbatim because that's not something that I can calculate right away. And so now what happens is, you might say, well, here I have again something that I can't really calculate, so did I really get something out of this complex calculation? And the answer is yes, because if you look at what you started from, our original form of the integral, so let's call this capital I, then what we have on the right hand side all the way down below here is again that same expression I. So in other words, what we've shown with this calculation is that I, the integral that we're interested in, is equal to pi over 2 minus I. So in other words, 2 times I is equal to pi over 2. And therefore I, which again is the integral that we're interested in, that is equal to pi over 4. So to wrap up, all of the manipulations are quite elementary, the rules and the calculations, but you see there's quite a difficult trick if you see it for the first time. What I recommend with integration is practice makes perfect, so do all of the problems that you have on the weekly exercises, try some of the extra problems, and generally just practice a lot, and you will get a feel for all of these rules.